Professor Vijay Gupta. He is a professor at Purdue of Electrical and Computer Engineering, and I'm going to hand this next talk over to him. So welcome him, everybody.
All right. Thank you. I am after dessert, but before the sort of the next talk from Sandy on darks and so on, I'll try to keep you awake. There's a bunch of phrases here in this title, and I hope that some of them will make some sense to you by the end. Let me start by saying why should we be studying game theory in the context of security? So like any term in popular culture, game theory has different meanings to different people, but any sensible definition of game theory would say it's a branch of decision theory which considers problems that have multiple decision makers that are self-interested, that care about some utility function or cost function that's assigned to them. That cost function might have a team component, but whatever that component is, we have to specify that. And after that, the agents already worry about their own utility function, that are strategic, that calculate what is going to be the effect of their action. And these are problems in which the utility that every player derives, every agent derives, is a function of what everybody else does. So take routing, for example. I want to minimize my own travel time, but my travel time depends not only on my decision, which is the route that I take, but on the route decisions of every other player as well. Right? So, it seems like that is a useful frame of problems. There's a useful class of problems. One can imagine problems in economics. One can also imagine problems in security, right? So in security problems, there is probably a defender and an attacker. There might be several defenders. There might be a hierarchy of defenders. There might be several attackers. There might be users. There might be many independent decision makers that are all making decisions according to their constraints and to satisfy themselves, right? And the utility that everybody derives is a function of what the attacker does, what the defender does, what the user does, and so on. So given that, why should it be, why is there sometimes a hesitation in using game theory in decision problems, right? I mean, that quote that I gave, a waste of time on a staggering scale, is sometimes quite openly said about game theory. And I think the problem is with us game theorists that we often forget that all game theory is a modeling framework. It makes asking some questions easier, and it looks at a problem in a way that makes those questions more obvious. Okay. So in cybersecurity, in particular, and security in general, there have been lots of works that have applied game theory, right? I mean, the GameSec is a particular conference that has been going on for 16, 17 years, focusing on Department of Defense applications. There have been textbooks and even respected labs, not just sort of academics with nothing better to do, but respected labs have come up with game theoretic interpretations and game theoretic frameworks to think about cybersecurity problems. So this is a attempt at a cybersecurity problem from somebody who's not in cybersecurity. So please pardon the overly simplified model. So let's think about a bunch of collections, and they might have a network in between describing how easy it is to go from one node to another. And the nodes need to be attacked by an attacker, has a limited budget, and what it wants to do is select which targets it should attack while deceiving the defender, while saying that the defender should not be able to detect it. On the other hand, defender also has a resource allocation constraint. Otherwise, it can just allocate as many resources as it can, and there is no attack that can succeed. And it should select a subset of targets to defend. Okay, this is a fairly non-controversial problem. Let's drop all pretense that I'm a cybersecurity researcher and model it by this particularly simple matrix, right? So the defender chooses one of the two rows. So there are now only two nodes, a node that is easy to attack and a node that is hard to attack. The defender needs to choose which node it wants to place its resource in, and the attacker needs to choose one of the columns. Should it attack the easy to attack node or the hard to attack? Okay? Now, what those numbers represent is the following constraints. If the attacker chooses the hard to attack node, 1 unit of its resources go away, right? That's just the resources it spends on accessing that node, right? So if the attacker attacks the easy node, it retains both of them. Now, if the attacker attacks the easy node and the defender defends the easy node, that's the first row and the first column, well, they meet head on, defender wins, 1 more unit of the resource attacker. Okay, the attacker starts with 2 units. It attacked the easy node. It retained both of the 2, but then it met the defender. So 1 unit of the attack was gone away and only 1 unit remained, right? The defender got 1 more unit because it defeated the attacker. And so in the 1-1 column, in this row, the first number means what the defender won. It won 1 unit. And the second number represents the advantage that the attacker had. It retained its 1 unit because it was attacking easy. On the other hand, if the attacker attacked the hard node, which is the second column, the defender defended the easy node. So the defender guessed wrong. Well, the attacker still lost 1 unit, but then it did not lose against the defender. So once again, this number represents that the attacker still has 1 unit left, one advantage left, and the defender could only win 1 unit from the attacker. Okay. So if the attacker went on the easy node, the defender guessed wrong. It went on the hard node. Defender didn't win anything, and the attacker had 2 units left, and so on and so on. Okay. It's a very simple game. And what it can model are, again, questions that we could have asked in the first diagram, the diagram up there, right? So in the diagram of the network, one could think about from the point of view of a defender. If the attack is the same as the attack on the Ukrainian grid from, let's say, 10 years ago, would our strategy succeed or not? On the other hand, the attacker could say, well, given this network and given a particular defender strategy, what is my attack? What should my attack be? And I can ask those questions in this overly simplified framework. I can add bells and whistles to this framework. I can add multiple steps of attacks. I can add imperfect information. But the point that I'm making would be clear even from this very simple example. I can say if the attacker attack is fixed, if the attacker is going to choose easy node, then where should the defender go? Well, the defender should go to the easy node. If the attacker wants to go the hard way, it's going to attack the hard node because that gives it more resources, then I should be defending the hard. Okay. So I can do the same questions that I could have asked in the diagram above through this simpler representation. Okay. But then you say, well, what is the advantage of game theory? Why should I why should I analyze my problem in this way? And the answer is that now the defender can start predicting what the attacker should do. Okay. The defender can say, well, the attacker is going to reason as follows. It's going to reason that if it attacks the easy node, then the defender is going to defend the easy node, and all it can do is get a benefit of 1. But if it attacks the hard node, then the defender is going to defend the hard node, and it'll get a benefit of 0. So attacker, if he is rational, is going to attack the easy node. So what it does is it allows us to go beyond particular assumed attack models and start reasoning. If the attacker is such that he's going to go for something minimum that he should always get, i.e. a rational attacker, then he'll attack the easy node. If the attacker is something that will go for broke, right? Either he gets 0 or he gets 2, then he'll attack the hard. And so given any extra information we have about the attacker, if this game is played once, we can do nothing but just kind of anticipate. But the network is not just there once. The network is out there. The defender will keep defending. The attacker will keep attacking. And over time, we can figure out whether the attacker is risk sensitive or risk neutral and so on, and then start reasoning about what the attacker is going to do, and hence what should I as a defender do. So it is this question, can I predict what the other player is going to do, how he is going to evolve, which is what game theory allows us to do. So just some terminology, because there were all those phrases. So this is a normal form game because I put it in a matrix form. I've enumerated the actions of different players. I've put in the utilities and so on. And I will emphasize that this is a particularly simple game. We can add dynamics to the game, multiple steps. We can add who goes first, who goes second. Not everybody goes together. We can add network structure, behavioral assumptions, and so on, and sort of ask the same kind of questions. So because this game is, let's switch to a normal form game that we have a little bit more intuition about, rock, paper, scissors. Right? Now, as I said, that if the game is going to be played only once, I as the attacker get to select which node I'm going to attack. You as the defender get to select which node we're going to defend. There is not much we can do. Right? We got to take our best shot, and that's that. The advantage of game theory is to consider games that are going to be repeated, that are going to happen again and again. Two players are going to play again and again. Right? So let's think about rock, paper, scissors. There is no optimal action that I can do if I'm just going to play it against you once. Right? I'll do something, and it's just a matter of chance who wins. But if we are going to play again and again, then what I need to think about is not an action in a particular game, but a strategy. How should I select my actions over time? Right? So I'll call that a strategy. And the question is, what strategy should I employ? So if you're playing against my daughter when she was 3 years old, all she could do was rock. Right? So it was, I was a father. I didn't want to win all the time, but I played against her 3 times, and I figured out that that's all she's doing. And so if I figure out the strategy that you're going to do, I can optimize my strategy. But as she grew older, she figured out that all I'm doing is playing paper. So now she thinks, well, I should mix it up with scissors. She starts mixing up rocks and scissors. Now, depending on how rational we assume the player to be, we can keep going, right? So first question I can ask is, if I identify the strategy that you're playing, what should I play, right? If you're playing rock all the time, I should not mix rock, paper, and scissors 1/3 of the time, which I will do against probably you, right? I should play paper all the time. I should identify. But then I can start reasoning about, are you adapting your strategy? And if you are adapting your strategy, how should I adapt my strategy? And in the limit, especially if we don't want to play this, this is a very high stakes game, I don't want to spend time identifying how you're updating. I can keep reasoning, assuming you to be perfectly rational. I can say, well, so you are going to reason that you should mix scissor with paper a few times because I'm playing paper. So then I should say, I will play rock and paper. But then you will know that, and you will adapt as well. And as I keep going, ultimately, I figure out that you are going to use rock, paper, scissors 1/3 of the time, and I should do rock, paper, scissors 1/3 of the time. That is mutually in equilibrium, right? And once again, this explicit focus on how is it that you are reasoning when I'm playing against you is sort of the central point of game theory. So this quote I really like. It was about chess that I first read it in. But it's really, the reason game theory is important, the reason game theory is useful, I guess, is because it provides a framework explicitly for thinking about what the other player is optimizing. So instead of saying that, let's take the attack that happened against the Ukrainian grid, and let's see whether our grid is secure or not, or our policy to secure our grid will work or not, we say, well, assuming that the attacker knows that this is how I'm going to be securing, because I'm going to be fighting, I'm going to be secure against the Ukrainian grid, he's instead going to attack this way now. Am I secure against that? If I change my defense, then he's going to come up with this better attack. And what is this final attack that I should be attacking, right? So 3 questions, right? Again, first, can I figure out what the strategy of the other player is? Design my optimal strategy. Can I adapt the strategy as the attacker is doing? And if it's a particularly high stakes game, then can I figure out in the equilibrium, ultimately, what is the optimal attack? And can I be robust to that? So oftentimes, game theorists would only talk about the equilibrium, but to me, sort of the life is not at equilibrium, right? Equilibrium is particularly boring, in fact. Life is always at non-equilibrium. What is the path to equilibrium is the question, right? as I play against you, can I figure out what you are playing? And how should I adapt my strategy in response is the question, right? So it's certainly clear that it's not enough to play best response to the last attack, right? That is just fighting the last war. That's because you are smart, you're going to figure out that's what I'm going to do. You're going to defeat me every time. I'm always playing with catching up, right? So instead, what I want to do is that, well, if you are like my daughter and you're playing a fixed strategy, I want to learn and be optimal against it. But also, if you are also adapting your strategy in this battle of wits, then I'm going to want to keep adapting till I reach this steady state of 1/3 paper, 1/3 rock, and 1/3 scissors, right? You may not be completing that equilibrium. You may say, okay, that's enough. That's what happens in chess, right? Players like me can only think about sort of one move in advance or something. The grandmaster might be thinking 15 moves in advance. So you want to figure out if it is the 15 moves in advance player, then you want to find out what the equilibrium strategy is and do the best against that. But if it's one move in advance, maybe there's much better strategies that you can do, right? So this field is called learning in games. It's kind of like reinforcement learning, except that the environment is highly non-stationary because the other player is also evolving, right? And one can ask the question, how should I learn, right? I mean, so I can think about this flow chart on the right? So I start from some belief of my opponent's strategy. I say, okay, if you're going to play rock, that's my assumption, then I should play paper. Okay, is that enough? Do you keep playing that? No. If that is enough, yes, we have found a solution. If not, then we go down here and we say, well, actually, you were not playing rock all the time. I come up with a better understanding of your strategies, update my own strategy, and keep doing this. And as I said, if at some point we keep doing this, we'll reach an equilibrium, but we can also stop at a non-equilibrium point and take into account the real attacker and the real defender that is there at any. Yeah. Do there exist such algorithms? Yes. It's a field of study 70, 80 years old. I believe fictitious play was introduced in 1951, and people have kept studying this, right? There are textbooks that have been written about this. Okay, so this is fictitious play. Fictitious play, not important to understand the details. All I want to say is that there are algorithms, and in this particular algorithm, for example, they maintain a belief based on your historical performance. Whatever you have played so far, I generate a histogram of that. I say you have played rock 80% of the time, paper 10% of the time, scissors 10% of the time. So that's my best guess of your strategy. And I keep evolving that based on more actions that I get. So that's a simple idea. It works, right? It works in the sense that, for example, if you apply to rock, paper, scissors, the actions that you will take according to that, you will converge to 1/3 rock, 1/3 paper, 1/3 scissors. It does not work always. If you can change around games and not converge, that's sort of an important problem, but I'll not talk about that. I would just say that it converges for many games with self-play. What does self-play mean? If both the players are doing fictitious play, then we'll both adapt to each other's strategies and converge to this equilibrium motion. And in fact, people have been expanding the class of games for which this applies. I stopped at 2005 because the slide stopped, but people have been working on extensions of this. So we have said, why might game theory be useful? Right? Because it allows us to think from an opponent's point of view. And we'll be much stronger if we put ourselves in shoes of the opponent and say, what are they looking at? What are they trying to exploit? And I've said this learning in games is important because that allows us to adapt the strategy to what our opponent's strategy is. Okay? Now I want to sort of go to the second part of the talk, which is going to be talking about this statement. It converges of the many games with self. So you might take umbrage at the fact that it's self. Right? So self-play means I'm doing fictitious play as a defender and you are doing fictitious play as an attacker. That seems too hardest assumption. Why should the attacker do something? He's my opponent. He might employ some other algorithm. So there are two ways of looking at this problem. The classical way of looking at this problem is that if fictitious play is put up against some other reasonable learning algorithm, the attacker is using some other algorithm, would we still converge or not? And there is research on that. For example, there is a different class of algorithms called no-regret algorithms, and that sort of against any other algorithm that has some loose properties will converge to equilibrium. So people are aware of that. I mean, we cannot possibly have all learning algorithms against all learning algorithms, huge number of learning algorithms, but people have been steadily chipping away at that assumption. So that assumption is not what I'm going to be talking about. Instead, what I'm going to be talking about is a different question that arises within that set, which is perhaps motivated by this experiment that people did. So this is an old experiment. This is actually a 1990 experiment, in which what they did was they paired people in two ways, right? So people are playing a game. There's the details of the game is not important. It's a card game. And first they said, you're going to play 50 rounds against the same opponent. Okay. That is, the results are out here. And as you can see, they converge to what the equilibrium is in pretty much every set. Right? They take some time, some more time or some less time, but they converge. In the second set of experiments, they said, in every round, you'll play 50 rounds, but in every round, we are going to randomly pick another opponent, and you're going to play against that. And once again, yes, a lot of times they did pick up sevens, but now you see that a lot of times they're playing some other strategy, which is not what is being predicted by theory, right? Remember the fictitious play. All I care about is the histogram. I don't care whether it's the same player or it's a different player. Right? But in a randomly picked strategy, I'm not doing that. A randomly picked player, sorry, I'm not doing that. I'm trying to perhaps go away from what might adapting the strategy to the best strategy. Why is that happening? So people puzzled over this. And in about 2000, there was this very interesting hypothesis that was proposed by Cameron et al., which is one of strategic teaching. So the strategic teaching says is that if I know I'm going to be playing against the same player again and again and again, I built a level of, I don't want to say trust, I try to confuse you about where we should go. While if it's a random player, I know anything that I do is not going to, the information is not going to be retained in the next round. So they define the strategic teaching as saying that players try to be sophisticated. They're not just blindly adapting their strategies. Human players especially try to be sophisticated in that they try to teach the other player. They try to confuse the other player. They try to guide the other player by choosing strategies with short-run payoffs. That may be bad for me, but then you'll get a model for me, which in the long run is really good. In other words, I'm trying to confuse your learning algorithm. And that is a pattern that has been observed in repeated experiment with human players. That I am not fine as an attacker. I'm not just okay exploiting the defense. I'm actually trying to deceive you into looking much worse, to much worse attacker. Because then when I finally attack, the payoff is going to be huge. Right? It's in soccer, right? In the entire tournament till the semifinals or till the finals, I might not play my trump card, because even though that's a rational thing to do, because I'm trying to lull you into a sense of security, a false security, and then I play my trump card, and that's a solution that really gets me through the part. So in the language of our learning algorithm, can I figure out what is the learning algorithm that the other player is using, and can I exploit that? Can I do the strategic teaching? And how do I do that? How do I reason about that? And on the other hand, if I'm using a learning algorithm to adapt my strategy, how do I prevent you from introducing this confusion into my learning algorithm? Okay. So the rest of the 4 or 5 slides are just sort of answers to these questions. But this is pretty much the point of this talk, right? So these two questions are really. Okay. So how do I do the strategic teaching? Well, it turns out that it's very, very easy to confuse standard learning algorithms. So think about this sort of normal form game. And you can show that if both players do fictitious play, you converge to what is the equilibrium. That's equilibrium I'm talking about is really a Nash equilibrium. And you converge to this. While if the role player does the strategic teaching, there is a way to do it. I'm not going to go into it, but simply think about the role player gets stuck here. It doesn't move. Then the other player, because of its learning algorithm, will converge to this long-term payoff, which is for the role player 3 instead of 2. So the first thing is pessimistic. It's very, very easy to confuse almost all learning algorithms. Is this a, perhaps the loss in performance is bounded? No, it's not. I can define the loss in performance through a ratio of, how much utility I can get by playing some other algorithm against your fixed learning algorithm, and there is no bound. Almost any algorithm, I can make it infinitely worse, the payoff, than what you would have gotten by me sticking to the rules, to the learning algorithm. In fact, there exist classes of games for which no algorithm has this guarantee. So this set of results is pessimistic. That if you are using a learning algorithm, be afraid, right? Be afraid, because the interpretation really is that we are opponents, we are playing defender versus attacker, and then there is a choice of learning algorithm. But that choice of learning algorithm is a strategy. And if I know your strategy, I can confuse you. That choice is very, very fragile to an attack. The actions that you take because of that learning algorithm and so on will be optimal in, given whatever your strategy is. But I have confused your strategy. This is perhaps a new avenue for attack. And so what it means is that I should really spend a lot of time trying to understand what the learning algorithm of my attacker is. So if I'm a defender, I should spend time on looking at the history of attacks, trying to identify strategy, but also identify how that strategy is changing, because that adaptation I can confuse. Right? I can confuse your strategy, but I can also confuse that there is information in this delta in how the strategy of the attacker is being updated, and that I can utilize to defend, and vice versa. If the defense is being updated in a certain way, that update strategy itself is fragile, and we should look at that. And we can pose a optimization problem in terms of how do, if I have no clue about what your learning algorithm is, we can try to just, it's very easy to set up math on that, just do sort of gradient descent based on actions. And here, sort of active learning becomes very important. I can purposefully launch weak attacks to see what your defense is doing and how do you update your strategy, how do you include that in. And I can figure out, just based on gradient descent and so on, the learning dynamics and obtain my optimal trajectory. So again, the interpretation is that choice of learning algorithms is a strategy. That strategy is fragile. I should exploit that. I should spend time on figuring out how do you update your strategies and use that. Can I prevent my learning algorithm from being exploited? So do there exist rational learning algorithms? The rational learning algorithms are simply one that do not have this fragility. One that if I'm playing a certain learning algorithm, I force you to play a certain learning algorithm as well and go to the equilibrium point that we originally thought would be good. So it turns out that, for 2-agent repeated normal form games, which was sort of why the title said repeated normal form games, we can set up this problem through, defining the long-term cost function now, right? Because we are interested really in a long term, the equilibrium does not go to something that we really not like, and come up with, sort of a way to make our learning algorithms into an exploitable one. And I'll not go through the details of this, but what the basic idea is that it is based on a threat. It's based on a threat that if I figure out that you're not using the proper learning algorithm that I thought, I would give up on my utility, and I'll just turn into a war against you. I'll just try to punish you any which way you can. All right? So let's try to cooperate. Let's try to have this learning algorithms in mutual sort of equilibrium and so on, because there is a grim trigger. There's a trigger that says, if I detect that something wrong, you're trying to confuse me, then I'm just going to punish you. It doesn't work for zero-sum games like security games, but for example, for deceiving games and things like that, it would work because those are not strictly zero-sum games. So it tries to explore and exploit. It's a classical exploration mechanism. It tries to figure out what the payoff matrices are and then keep following the desired learning algorithm. If it detects a deviation, there is a trigger that is pulled, and that trigger essentially forces the other agent to play, to not to confuse us too much. So there is without going into kind of introducing notation and so on, the basic idea is just to think about a grim trigger strategy, right? So, and it will work for a non-zero-sum game. For a zero-sum game, it doesn't work, right? Because it's anyway, I'm punishing you anyway. Okay, and we can prove that this algorithm will work if this punishment is harsh enough, right? So if the punishment is harsh enough, you will play by the rules, and you will not exploit my learning. And we can consider stochastic games and so on, but there are some limiting assumptions here that I can observe all the actions and the rewards that you are getting. So there are some technical assumptions, and again. All right, so this is all I wanted to say. So two main points. One is that games are relevant because, without falling into love with the beauty of our game models, and it's really, we should think about that this is a modeling framework which allows us to ask some questions and give us some insights. And the specific insight that I think I focused on today was that the other player also gets a vote in terms of what the outcome is. And we should think about what that other player is doing, how they're updating their strategies, and so on as we update our strategy. And in particular, the choice of these learning algorithms of how to update the strategy is also a strategy. And so it is fragile. It is prone to these poisoning kind of attacks that somebody can confuse us. And so we should exploit that to the maximum. And we should also try to be aware of this possibility and use more sophisticated learning algorithms. That's all I wanted to say. Thank you for your attention, and I'll be happy to take questions if time permits.
We're out of time for questions. Thank you very much. I believe we are going into break now.